I'm Michael, and today I'm going to walk you through 7 mistakes that I see people make constantly when they're setting up their off-grid solar systems. And trust me, some of these mistakes are costing people hundreds of dollars they didn't need to spend. I've worked with a lot of solar setups, helped people fix systems that just weren't performing, and the same mistakes keep showing up again and again. So let's break them down one by one. The first one is undersizing your entire system. This one is probably the most common mistake, and it hurts people right from the beginning. Most beginners just guess how much power they need. They pick a battery, grab a couple panels, and then wonder why their system dies by 8 p.m. Before you buy a single component, you need to sit down and do a proper load analysis. Write down every device you're planning to run, and next to each one, write its wattage and how many hours per day you'll use it. For example, say you're running an air conditioner that pulls 1,600 watts and a microwave that pulls 1,400 watts, and at some point, both are going to run at the same time. That means your inverter needs to handle at least 3,000 watts, and that's before you even factor in surge power at startup. A lot of people skip this step. Don't be that person. Getting the load analysis right saves you from buying everything twice. The next one is using low battery voltage for high-power systems. This one catches people off guard because it's not obvious until you look at the numbers. Let's say you're running a 3,000-watt inverter on a 12-volt battery bank. To deliver that power, your system has to push around 250 amps through the cables. Add a proper safety margin, and you're looking at over 310 amps, which means you need seriously thick, expensive cable. You need a 2-aught welding cable, which can easily cost you $100 for just 20 feet. Now switch that same 3,000-watt inverter to a 48-volt system. Suddenly, you only need around 63 amps with safety margin, about 80 amps. A 6-gauge cable handles that just fine, and it costs around $30 for the same 20 feet. Same inverter, same power. But the 48-volt system saves you real money just on wiring alone. Here's a simple rule I follow. 12-volt battery inverters up to 1,200 watts. 24-volt battery inverters up to 2,400 watts. 48-volt battery inverters up to 6,000 watts. The same logic applies to your charge controller. For 1,000 watts of solar on a 12-volt system, you need a controller rated for around 70 plus amps that can cost you close to $380. The exact same 1,000 watts on a 48-volt system? You only need a 20-amp controller, which runs around $180. That's less than half the price. Higher voltage isn't just for professionals. It's the smarter, cheaper choice for anyone building a serious system. The third mistake, undersized cables. Now here's something that people often overlook after they've sorted out their battery voltage and inverter size, the cables connecting everything together. Undersized cables don't just hurt your system's performance, they overheat. And an overheating cable in a DC system isn't just an inconvenience, it can melt, arc, and in the worst case, start a fire. Here's something most beginners don't know about cables. They come with different insulation, temperature ratings, 60, 75, 90, and 105 degrees Celsius. The lower the rating, the less current that cable can safely carry at the same thickness. So, two cables that look identical can have very different safe current limits just based on their insulation. My recommendation: use welding cables wherever possible. They carry higher temperature ratings, which means for the same physical size, they can handle more current than standard cables. And one more thing, when you're buying cables, watch out for anything marked copper-clad aluminum. It looks like copper on the outside, but conducts significantly less current than pure copper, and degrades faster over time. Always go with pure copper-stranded cable. It costs a little more up front, but your connections will be cleaner, safer, and last much longer. The next is using the wrong fuses. So now your cables are properly sized, but are your fuses right for your system? Because this is where things get genuinely dangerous if you get it wrong. A lot of people just grab whatever fuse fits physically, and that's a serious mistake. In DC systems, fuses aren't just about the current rating. They also have a voltage rating, and this one really matters. For example, a standard mega fuse rated for 32 volts cannot be used in a 48-volt system. Why? Because a fully charged 48-volt lithium battery can actually sit at around 58 volts. That fuse was never designed to interrupt that voltage, and in a fault condition, it can fail to protect your system entirely. The interrupting current capacity, or ICC, is equally important. This tells you the maximum fault current the fuse can safely stop. Here's a real example. A 12-volt, 100 amp-hour lithium battery can push around 1,000 amps during a short circuit. That's roughly 10 times its capacity. A standard MIDI fuse handles up to 2,000 amps at 32 volts, so it works fine for a 12 or 24-volt setup. But scale up to a 48-volt, 400 amp-hour lithium battery. Now you're looking at potential short-circuit currents of 4,000 amps. Standard MIDI, Mega, MRBF fuses won't cut it. You need a Class T or NH0 fuse, something rated for both the higher voltage and the higher fault current. Match the fuse to your actual system voltage and battery size. Don't just grab what fits. Mistake number 5. Using cheap lugs. All right, cables are sized correctly, fuses are matched properly. But there's one more connection point that people cheap out on constantly, and that's the lugs crimped onto the ends of your cables. I've tested this myself. A cheap lug costs around 25 cents and weighs about 2 grams. A quality lug costs around $1 and weighs nearly double that. The weight difference alone tells you the wall thickness is completely different. Here's the problem with thin-walled cheap lugs. When you crimp them with the correct die, they don't compress properly onto the cable. The lug just pulls right off. That means you have a connection that looks fine on the outside, but is actually barely making contact. That's how you get resistance, buildup, heat, and eventually a failed connection, or worse. A quality lug with the same die compresses properly, grips the cable solidly, and stays put. Spend the dollar. Use lugs that cost at least $1 each, and this same rule applies to ferrules and ring terminals. Stick to branded materials from reputable suppliers or your local hardware store. It's one of the cheapest upgrades you can make, and it directly affects the long-term reliability of every connection in your system. Mistake number 6. Using non-branded fuses and breakers. Now, we just talked about using the right fuses, but there's another side to this that's just as important. Even if you've matched the voltage rating and the current rating correctly, if the fuse or breaker itself is a no-name cheap component, that rating means absolutely nothing. Here's why branded fuses and breakers go through actual independent testing. The numbers on the label are verified. A no-name component from some random listing? That interrupting current rating, that voltage rating, it's basically printed on there with zero accountability. Nobody tested it. Nobody certified it. And the scary part is, you won't know it's failed you until something actually goes wrong. By then, it's too late. Stick to trusted manufacturers' brands like Bussmann, Littelfuse, Blue Sea Systems, Siemens, or Schneider. These companies have been making electrical protection components for decades. Their products are tested, certified, and actually do what the label says. Your fuses and breakers are the last line of defense between a fault and a fire. Don't compromise on them to save a few dollars. The last one, battery's discharge rate. And finally, this one doesn't get talked about enough, but I see it destroy batteries all the time. Every battery has a maximum discharge rate, and pushing past it actively shortens your battery's life. Lead-acid batteries have a maximum discharge rate of 0.2 C. In real terms, a 12-volt 100 amp-hour lead-acid battery can only safely deliver around 20 amps. That's about 240 watts of continuous load. Connect a 1,000-watt inverter to that, and you're pulling over 4 times the safe limit. Sulfation builds up, capacity drops, and that battery is dead way before its time. Lithium handles this much better. A 12-volt 100 amp-hour lithium battery at 1C can deliver up to 100 amps, comfortably supporting a 1,000-watt inverter. But push past its limit, and the battery management system will shut it down. And that shutdown will always happen at the worst possible moment. Simple fix: check your battery's data sheet before connecting anything. Match your load to what the battery can actually handle. 5 minutes of checking saves you hundreds in replacements. So there you have it. 7 mistakes that can silently kill your off-grid solar system. Get these fundamentals right from the start, and your system will run reliably for years. If you've made any of these mistakes yourself or think something should have been on this list, drop it in the comments. I'd love to hear it. And if this helped, hit that like button. I'm Michael. This is Battery Hacker. See you in the next one.